Hello, everyone. Good morning, good afternoon, and good evening. My name is Natalie Villalobos, and I'm a community manager here on Google+. And today I'm really excited to bring you the opportunity to meet with some scientists from the CERN CMS project. And these are physicists who are working on the frontiers of particle physics. And they're here to have a conversation with us here on Google+. They're doing research on the Higgs boson particle. And we're pleased that Google+ is a platform for really intelligent and engaging conversation. With that, I would like to pass the floor off to Dr. Joe Incandela, joining us from the CERN CMS project, and Ann Koay.
Hi, everyone. So I'm down here. Can you hear us okay? I can hear Ann. Yes. So I'm just going to tell you where we are, and I'll let Ann talk a little bit because I spoke most of the time in the last. But I'm 100 meters underground, 300 feet underground, so 30 stories, with the detector. And Ann is up above on the surface in the control room of the detector. So Ann, why don't you tell them a little bit about what it's like to do particle physics, anything you like, but what's going on in the control room for that matter. And
well, I think
we could take some questions.
So if you can see behind me are a bunch of screens. Basically, this is a room just full of screens and people who are monitoring the detector as it runs. And in fact, right now, I think we might be taking cosmic ray data, which is no collision, so they're just particles coming in from outer space. And if you can see, there are some physicists around, but maybe it's hard to get them on the screen. They're basically focused in their work.
Yeah, this is the first day we have the detector running again after about 2 months off. We did maintenance. And, we're getting ready for Beam, which will come in about another month. So we take some questions. I see the school has joined us too. This is great. This is Tudor Vianu National High School for Computer Science, Bucharest.
Hello.
And, maybe we could take some questions. Cliff?
Me? Yeah, I've been, well, thanks a lot for having me. I've been studying a lot of quantum field theory and stuff, so I'm starting to get a little bit of an idea about all these things. And I'm just trying to get an idea of like what the most interesting problems you actually solve are. It seems like a lot of it comes down to how to like cut the data, both at like the trigger and designing like the right bins and the right widths and everything. So I'm just curious, I don't know what the right specific question to ask is, but I'm just curious like what's the most interesting aspect of doing that, or like how do you go about doing that, and what parts of it are challenging and interesting?
I'll let Ann answer about the trigger, but I was going to say you're studying quantum field theory on your own?
Yeah, well, I have a physics degree, and I'm not in grad school, but I'm kind of pretending that I'm a grad student, and I'm teaching myself a lot of standard model stuff, and, you know.
Very good. Ann, why don't you tell them how the trigger works and what's exciting about it?
Triggering? Well, I think that most physicists don't consider triggering as the most interesting part of their jobs, but it is, in fact, a most necessary part of our jobs because we do not take every collision event that happens in the detector and record it. That would be too much data. So a lot of the discarding of events already happens immediately once the collision event occurs, and it happens in the detector. And we have to throw away most of our data and keep only the interesting events. So the basic task in trigger design is to find a simple way to identify whether or not the event is interesting for us to keep. And we cannot run complicated algorithms like we can do offline, so everything has to be very fast and very simple, but still has to select exactly the physics that we want to record. And so, for example, you can look for events with an interesting particle, a high energy jet, or anything else that you might imagine.
Yeah, we have to keep it really simple. So we use simple patterns of energy, for example. And like Ann said, we get 15 million collisions per second, and we keep 300. So imagine how carefully you have to, and how fast you have to make decisions. But you're right. That's a big part of the what we do. I see there's another question here coming in.
Yes.
Shall I?
Do the four known interactions cover the entire range of distances that we can probe? Tudor Vianu, High School of Computer Science in Bucharest.
Right. So you're asking if the four known interactions cover the entire range of distances that we can probe.
Yes.
So the four known interactions, in some sense, yes, that's probably the right answer is yes. It's a complicated question, but we use different interactions, but mainly we use nuclear interactions in what we do the study. So we're colliding protons with protons. Protons are nuclear particles. They're made up of quarks and gluons. And they interact via nuclear forces, either the strong nuclear force or the weak nuclear force. That's two of the four interactions that you mentioned. And what distance we probe really depends on the energy. It's very much like a microscope. So if we can go to higher and higher energy, we can probe smaller and smaller distances until we get to a certain point where distance doesn't make any sense. That's what's called the Planck length scale. But that's so far away from anything we can reach right now that it's not even worth really worrying about. There's a lot of background noise. I don't know where it's coming from, but...
There's background noise coming from one of the cameras. If you guys have a lot going on, I can only kind of hear the machine. If there's background noise, feel free to mute yourself in the upper right-hand corner, and that'll help us keep the conversation at a really nice quality level. But yeah, but then again, my friend was just telling me, make sure to unmute when you want to ask a question. M. Jennings or Ioana, do one of you guys have a question?
Hello. Greetings from UK.
Ladies first. Ladies first. Go ahead.
Ioana.
Yes, I would like to ask if are you intending to make a prediction for the Higgs boson in the near future?
Well, you mean are we? Well, we don't really. We're experimental physicists, so we don't make predictions. We make measurements. The predictions are all made by the theorists, and so we're hoping to have. We just released a lot of results. In fact, just last week we submitted 5 papers on the Higgs, but the results were already known publicly. Now we're going to get about 4 times as much data in the coming year. So about a year from now, we hope to have actually new papers that really do talk about measurements of the Higgs itself, actual observation of the Higgs and the discovery of the Higgs. Or we'll be able to rule out the standard model Higgs, which is one version of the Higgs which is the most favored. So yeah, in about a year you'll see some major results. But we're looking for other things as well.
Thank you.
Okay.
Ioana,
Yeah, I have a
question. Oh, go ahead.
Oh, go ahead.
Ioana, go ahead.
Thank you. We thank you very much.
What is your question?
I think she's just grateful. Perhaps is Ioana. I think you work with Vladimir's school, perhaps.
There were 2 of my students. Thank you very much.
Okay, cool. Thank you. So, Vladimir, do you and your students have some questions for Dr. Jones?
We actually do.
Good.
Hello? Can you hear us?
You're good.
Can you hear us?
Yes.
Yeah.
Okay. We're part of the Society of Physics Students Club, so we're all our undergraduate students from the University of Rochester. And we have a question. The first question we had was, actually, is it possible for you, Doctor, to rotate the camera so we could see like more of the experiment?
Sure, I was going to give you a little tour. You work with the University of Rochester. I have one of my colleagues is from the University of Rochester. I work with closely.
For the first part of the Hangout, Professor Garcia Bellido was actually with us here.
Who?
Garcia Bellido.
So we're showing you around the detector a little bit now. You see this green thing and yellow, that surrounds the beam pipe. So the beam comes in from where the green is toward the yellow and then into the detector. And those are shields, actually, to protect the detector from particles. And if you go further over, you see a big orange thing. You see that?
Yeah.
Oh, let me see if I can aim it right. That, look, I can handle it. So that thing there is actually, oops, I don't want to shut down. That is another shield that's actually a door. If you look at it, you can see there's a big hinge. And that shield closes around the green shield, and that's 100 tons. So it's actually 220,000 pounds on one hinge, which is pretty impressive. And it swings shut, but it's not shut yet. And then in this direction, you can see actually the detector itself. If I go further and further that way, you can see more of the detector. It's hard to see it because there's a lot of things in the way, but those are all electronics racks. If I can show you. Yeah, so you can see the hallway down there. The detector is about 60, 70 feet long and about 50 feet tall. It's a little hard to see now because it's all closed up very carefully. Anyway, there's a little tour.
Oh, that's great. Can we ask another question?
Yeah.
So, when you were approached with the rumors about the creation of black holes...
Speak up a little bit, though.
Hello?
I'm having trouble hearing you a little bit.
When you were approached with rumors about creating black holes in the collider, how did you respond to that?
How did we deal with it?
How did you respond to that? What did you tell people?
Okay. Maybe Sue Ann can answer that.
You leave the hard questions to me then. Well, I think the probability of creating a black hole in our particular collisions is extremely small, smaller than even the probability of creating one from cosmic ray particles. So it just was not a huge risk factor, for example.
In fact, we're hoping to make them, okay? To tell you the truth, we're hoping to make them. We're looking for them all the time. But we're looking for safe black holes, the ones that immediately decay and explode into interesting particles. In fact, the ones that people were worried about were the ones that would live a long time and start, slowly eating the planet and things like that. But those black holes, the whole concept of a black hole that would be produced here that could do that is, for one thing, we know it doesn't happen because it would have happened with cosmic rays, as Sue Ann said, and we would have already destroyed the planet, possibly, or we would have seen evidence of this kind of thing in the universe that we don't. And also it violates a couple of laws, really, that we don't think are violatable, if you like. But yeah, we're hoping to see some, but it's also very improbable. I think we have to go to higher energy to start seeing the ones that might be produced. By the way, the only way we could produce them here would be if there were additional extra dimensions. Okay, if there were extra dimensions, spatial dimensions, that's part of the needed ingredients, and there's no evidence for that yet.
So I have a question for you. During this year, as you close in on the Higgs boson hunt, you're expected to go to 4 tera electron volts, but I understand that shortly you'll be shutting down and upgrading everything. Will that affect CMS at all during the 2013 upgrade shutdown? Are you guys going to do anything to magnet-wise or anything like that?
Yes. So just so everyone knows, we ran with beams of 3.5 tera electron volts last year. And this year we're going to 4, so the collision energy will be 8 instead of 7, because the beams collide head-on. And we'll run for a year, and then everything goes off the air for 2 years, roughly 2 years. And in that time, they're going to upgrade the accelerator so we can go to 13 tera electron volts collision energy from 7, and look for those black holes, okay, amongst other things. But CMS will make some improvements as well, but most of the detector is ready to go. We could we could run at the higher energy. We were designed for that higher energy, and we're pretty much ready to go. But in that 2-year period, we'll do quite a bit of work. We'll actually add some systems and improve some of our electronics and fix things that don't work as well as we had hoped they might. But things work extremely well, so we're in pretty good shape.
Oh, and I would like to pay you guys a compliment. Thank you for allowing me to have access to your web pages. For those people who don't know, I'm not a physicist. I'm just a fan of physics, and I have a web page that pulls together probably 55 different live displays that you saw her show in the room that's going on, so you can view them in real time on the web. And thank you very much for being such a public, sharing your information, because it's a lot of fun to watch CMS collisions actually happening and Atlas and things like that. So thank you very much. I appreciate it.
That's great. We are really interested in learning, and our goal in the world really is to try to understand things. And what we do is for the benefit of everyone, and we try to make it very public. And we're glad that people are interested. This is fantastic.
Oh, yeah.
Hi, Frank here, the green blob. That's unfortunately my camera got chopped up by a black hole. You mentioned like numbers and energy levels that are incomprehensible to, well, laymen. And my question is there any damage done by the collisions to the actual equipment you have? Does it burn holes during those experiments, or is it capable to handle those kinds of explosions that are going on?
It's a good question. We produce these collisions of very, very energetic protons, and very high energy particles come out, and they pass through our detectors, and they cause radiation damage. They actually can damage the nuclear structure of some of these materials. I should tell you, we're not producing like nuclear explosions. The amount of energy involved is really rather small, and it's not dangerous to humans at all, in the sense that we're down here now and the beam's not running, but there's not a lot of radiation left over at this point and so forth. But these particles that come out, where they hit the materials, they actually can cause some damage, and over time we accumulate damage. And so we had to spend a lot of time. We spent maybe 10 or 15 years learning how to design materials and detectors that could withstand that kind of damage. And we call those radiation hardened, radiation tolerant materials, and radiation tolerant detectors. So you're absolutely right. It's a big concern for us because we have to run this detector now for 10 or 15 years. And it took us a long time to figure that out. I could tell you more, but it would become very, very technical. But it is a good point.
And do you have a replacement cycle for some components during that time, or?
Yes, that's another good point and a good question, because it took us 10 or 15 years to design the current system, and we already know that in 10 years from now we're going to go to much higher radiation levels, and so we're doing R&D now, research and development into new materials. For instance, where we used to use silicon for detectors, where we're using silicon now, and we developed silicon that's very radiation hard. In the future, we might have to use diamond. Diamond is extremely radiation hard. It withstands radiation extremely well. So, diamond is a physicist's best friend as well as a woman's best friend, perhaps. But we're doing all kinds of things like that. So we're looking at all kinds of new materials, new methods. Some things we may just have to keep replacing every year because they'll just get so much radiation. The things that are very, very close to the beam see the most radiation, right close to the collision.
So I had kind of a follow-up question. So I'm Jennings. You said you had a website that was pulling in all this great publicly available data. Actually, so are there other kind of citizen science projects, people like M. Jennings? Are there other people that are creating new and interesting findings that support what you guys are doing? Do these projects have names? Are there other ways that people who are interested in physics can get involved with the experiments that you guys are running?
There's certainly going to our webpage. We have lots of resources. We do lots of outreach, education and outreach. We don't have a lot of people that work on that and a lot of money. We actually, even though it looks like what we're doing is very expensive, which it is, we're always short of money. So we do what we can with very little budgets. But there are many things we're doing and that CERN are doing that are very interesting. One project they have is to have many high schools around the world looking at detectors, having detectors with that detect these cosmic rays that I was telling you about, these muons coming from outer space. And so we're trying to set up many high schools around the world to actually correlate the information, because even though we've studied cosmic rays in the field for many, many decades, actually for almost 100 years, no one's ever asked if something happens that's correlated for the north hemisphere and the southern hemisphere. But sometimes something will hit the upper atmosphere and produce muons, these particles that shower all over the place. So there's some interest in seeing if the northern and southern hemispheres could see events that occur simultaneously. And we're doing that with high schools, okay? And this would actually be very, very interesting. And there are many, many other things like this, but you have to go on our websites and dig around, and you'll find things you can do. And there are many physicists that would be also interested in helping high schools and things like that in getting involved in these things.
Awesome.
And can I...
Go ahead. Yeah, follow up.
Can I add that for citizen, shall we say, participation, that website that I made that I'm talking about, meltronics.com, probably the top 2 users are Brookhaven Labs and CERN use it the most, and a lot of people all over the world are just interested in what you're doing. And I built this on purpose this way to support the Director General's idea that CERN was involved only in producing pure research papers, on the subject. And so I decided to pick up the slack, which was keep the public informed, show them what's going on and things like that. So I'm kind of the citizen advocate for CERN, and once again, thank you it's been an experience, and to watch those collisions every day is just awesome. Thank you.
That's great.
Oh, sorry, Joe. I was going to ask a question from the stream, but do you want to go ahead?
No, go ahead. Go ahead.
So, Don DeHare, I hope I'm pronouncing that right, he asks, could a facility like this be feasible in space?
Sven, it is. Why don't you explain that, Sven? There are detectors in space.
Whether you want an accelerator in space.
But it is. AMS does that.
Yeah, there are what are called cosmic ray detectors that go into space. But the CMS detector behind me, just to give you an idea, is 14,000 tons. So it weighs twice it has twice the weight of the Eiffel Tower. So to put that in space would cost probably a few $100 billion. I don't think we'd get that money. But if you know anybody that has it, that's willing to give us that money, we'll be very happy to take it.
Yeah, but where would you put your shifters?
No, they'd have to become astronauts. So you'd have to learn, how to walk in space to it.
Yeah, that would be nice, actually.
There are many experiments done in space. Particle physics, we do particle physics in space with fixed detectors in satellites. We do particle physics experiments underground. And we do without accelerators in both cases, just looking at particles in space. And then we have particle physics experiments where we actually produce beams. And the beams are what we do here. And that's the most easily controlled, of course. But Mother Nature can sometimes produce particles that are much higher energy than anything we could imagine. That's why we like these other experiments that float around in space, looking for interesting things.
Just a question: is the amount of gravity that you have on Earth, is that of relevance at the high energy levels you're running it at, or not really?
Well, Suen is trying to understand gravity
Yeah, I think you once told me whether we could design an experiment to measure the gravitational force at an accelerator like this, and I couldn't figure out a way to do it because the gravity is such a weak force compared to electromagnetic forces and the strong interaction that's happening in this scale. So basically there's no effect from gravity.
Gravity is so weak it takes a whole planet to hold you down, and then you can still jump.
Okay, so from that perspective, going into space is not the benefit.
There are some potential benefits of going into space. If we built an accelerator on the moon, we wouldn't need to refrigerate it because it's already cold. Things like that.
Okay, yeah.
So I think everyone had a chance to ask a question. I want to say thank you on behalf of the Google Plus team. Really, I'm sure the whole room, can say the same thing. This has been an incredible opportunity for all of us. Any closing thoughts from any of the participants?
Nope. Great.
Keep up the good work.
Yeah, do it again.
We'll do it again. This is the first time, at least that I've done it, and we're looking for ways to actually make more contact with people and have them understand what we're doing. Because I should say that just in general, I find even though what we're doing is really at the far, far reaches of knowledge, and so has really no application whatsoever, many people are very interested because it's so fundamental and it tells us about where we are, who we are, what this place is, what this universe is, more and more. And we want to connect more people to that if we can. There's no doubt about it. We need to recruit more brilliant young physicists like Suan. So this way
can I add a little comment here? My website, which is just like I told you, the panels that go into Make CERN, has something like 60 countries hitting it a day. We get all over range of people, from scientists watching it at night to the average person just sitting down. I've had people tell me we just put it on the TV and watch it at night. So you have quite a following that bigger than I think you think it is. It's really quite large. So keep it up. You're doing good stuff and reaching the right audience.
Yeah, and I didn't mention this at all in the whole discussion, but we're very, very international. The experiment that's behind me, almost everything you see is built by someone from some different country. We have 40 different countries involved in the experiment, from 180 different institutes, and we work together extremely well. And that's another story that we don't have time to go into now, but the collaboration of people from 40 different countries, often countries that are very hostile to each other, but scientists who get along extremely well. We have our small problems from time to time, but it's an amazingly positive collaboration, and it's another story that I think CERN is very important for the world in that sense. We show that people can work together and do great things, no matter where they come from. So thanks very much to Google Plus as well. This was a great experience for us.
Thank you.
Thank you all for being here, and looking forward to seeing more from the CMS CERN page here on Google+. From here in Mountain View, we hope everyone has a great morning, afternoon, or evening, wherever you may be.
Yeah, it's almost 8:30 p.m. here, so take care, everyone.
Thank you. Good night.
Thank you. Bye-bye.